Bismillahirrahmanirrahim. Assalamu alaikum. In our today's video, we will discuss about ideal derivative compensation and lead compensation in depth. So let's start. Transient response of a system can be selected by choosing an appropriate closed loop pole location on the S-plane. One way to speed up the original system is to add a single zero to forward path. Transient response unattainable by a simple gain adjustment can be obtained by augmenting the system's poles and zeros with an ideal derivative compensator. The transient response of a system can be selected by choosing an appropriate closed loop pole location on the S-plane that I already described, but if this point is on the root locus, then a simple gain adjustment is all that is required in order to meet the transient response specification. If the closed loop pole location is not on the root locus, then the root locus must be reshaped so that the new root locus goes through the selected closed loop pole location. In order to accomplish the latter task, poles and zeros can be added in the forward path to produce a new open loop function whose root locus goes through the desired point on the S-plane. One way to speed up the original system that generally works is to add a single zero to the forward path. This zero can be represented by a compensator whose transfer function is given as g sub s. This function, the sum of differentiator and a pure gain, is called an ideal derivative or PD controller. The position of compensator 0 can quicken the response over the uncompensated system. In summary, the transient responses unattainable by a simple gain adjustment can be obtained by augmenting the system pole and zero with an ideal derivative compensator. We now show that the ideal derivative compensation speeds up the response of system with the help of different examples. In this example, here several examples are shown in this figure with an uncompensated system in figure A operating with a damping ratio of 0.4 becomes a compensated system by adding a compensating zero at -2, -3 and -4 in figure B, C and D respectively. So in each design, the zero is moved to a different position and root locus is shown for each compensated system. The dominant second order poles are further out along the 0.4 damping ratio line than the uncompensated system. Each of the compensated cases has dominant poles with the same damping ratio as the uncompensated case. Thus, we predict that the percentage overshoot will be the same for each case. Also, the compensated dominant closed loop poles have more negative real parts than the uncompensated dominant closed loop pole. So, in this figure, the step response comparison has been done. This is the uncompensated system. These are three different cases with 0 at -2, -3 and -4. So we'll solve another example in which the ideal derivative compensator design has been used. We have to design an ideal derivative compensator to yield a 16% overshoot with a threefold reduction in settling time. This is the solution of the example. So first we will evaluate the performance of the uncompensated system with 16% overshoot. The load locus for the uncompensated system is shown in this figure. So since 16% overshoot is equivalent to the damping ratio of 0.504, we will search along the damping ratio line for an odd multiple of 180 and find that dominant second order pair of pole is at minus 1.205 real portion, and this is the imaginary portion, so complex conjugate poles. Thus the settling time of the uncompensated system will be 3.320. To compensate a system, first we find the location of compensated system's dominant pole. To have a threefold reduction in the settling time, the compensated system settling time will be 1.107. Therefore, the real part of the compensated system dominant second order pole is, this will be the real part, and this will be the imaginary part. So evaluating the location of compensating zero, thus the sum of angle from the open loop pole to the desired dominant pole will be this one, minus 275.6. Hence, the angular contribution required from the compensator zero for the test point to be on the root locus will be plus 275.6 degree minus 180 degrees, that is 95.6 degree. The geometry is shown in this figure. Where we now must solve for the negative real portion, the location of the compensator zero. From this figure, we can see that 6.193 divided by 3.613 minus the real portion. So this will be equal to the tangent of 180 minus 95.6 degree. Thus we will get the real portion 3.006. The complete root locus for the compensated system is this one. So this is the uncompensated and compensated system step response. Now we will discuss the lead compensation. An active ideal derivative compensator can be approximated with a passive lead compensator. When passive networks are used, a single zero cannot be reduced, rather a compensator zero and a pole result. If the pole is further from the imaginary axis than zero, the angular contribution of the compensator is still positive and thus approximate an equivalent single zero. If we select a desired dominant second order pole on the S-plane, the sum of angles from the uncompensated system's pole and 0 to the design point can be found. The difference between 180 and the sum of angles must be the angular contribution required for the compensator. For example, looking at this figure, we see that there are 5 angles from theta 1 to theta 5. So sum of zero's angle minus sum of pole angle should be the odd multiple of 180. So this is theta 5 and this is theta 2. This should be positive and the angle of poles that are theta 1, theta 3 and theta 4 will be negative. So 0 angle minus pole angle should be the odd multiple of 180. Theta 2 minus theta 1 is equal to theta c, the angular contribution of the lead compensator, because these are the compensator pole and 0. How do the possible lead compensators differ? The differences are in the values of static error constants, the gain required to reach the design point on the compensated root locus, the difficulty in justifying a second order approximation when the design is complete, and ensuring transient response. For design, we arbitrarily select either a lead compensator pole or 0 and find the angular contribution at the design point of this pole or 0 along with the system's open loop pole and 0. The difference between this angle and 180 is the required contribution of remaining compensator pole or 0. This is our today's discussion of PD and lead compensator. Thank you very much.